Hello world and welcome to Learning Java, one byte at a time. This is video 17 in a tutorial series geared at bringing the wonderful wide world of Java to those with little or no programming experience. Now in the last two videos we talked at length about variables, and in this video I hope to sort of wrap up the discussion, and I hope you'll agree that there really was a time and place to bring up this content laden subject, and certainly not at the very beginning of the Java journey, but after we've had our fingers in the fundamentals of the code and after we've worked with it and we have a little context and a little background about exactly what Java is, I feel like it's just so much more easy to retain, and I hope you'll agree that this was the right time and place to talk about it. And so in this video I want to talk a little bit about casting and what it means to convert one data type to another one. And so in Java there are two different types of casting. There are what are called implicit casts and explicit casts, or narrowing or widening variables. And you can probably derive by the way that they're phrased exactly what's going on, but this is essentially taking the capacity for your variable and either trimming it down or making it larger. And so if you start with a smaller variable type, like if you start with a byte and you widen a byte into an integer, you're not going to lose anything. You're going to add a little bit more depth to the variable, but you're not going to add any more information because the information wasn't there to begin with. Now if you do the opposite, if you take an integer and you whittle it down to the size of a byte, you'll make it into a byte, but you're going to have potential data loss. And so if you have something that's going to be 10 or 11 digits long, and you bring it down to something that's only going to be 3 digits long, then all of that excess data is going to be lost. Now, if it just so happens that it's all zeros, you haven't really lost that much, and there may be cases where the loss is acceptable. But just keep in mind that the widening of a variable doesn't do anything except for add the extra capacity for information. But of course, if the information wasn't there to begin with, it's not going to be carried through. Whereas the narrowing of a variable is going to trim it down to size, but if there was information there, that information will be lost. And Java typically does a good job of rounding, although there are some quirks, there are some interesting behaviors that happen when Java does these castings, and it's also important to bring that up and talk about that. And so, without further ado, let's go ahead and jump into the Notepad++ application, and we'll start to review the proper way to do the casting in the Java programming language, and we'll also run the program and we'll look at some funny, quirky behavior that happens when Java attempts to do its best job at rounding this data. And so here I have a class called casting, and in this class I have declared several numerical data types. I have a byte called myByte, a short, an int, a long, a float, and a double. And so the 4 integer data types and the 2 floating data types. I've also declared a car data called myCarLiteral and a car data called myCarNumerical. I also have 2 booleans. I have a boolean literal and then a boolean conditional, and we'll talk about what those are for in just a moment. Here in my main method, I've went ahead and assigned the variables I've declared their values, and so I've assigned the byte the value of -120. The short has a value of +129, and if you remember, the byte goes from -128 to +127, and so I purposely put that out of the range of the byte, but well within the range of the short. My integer has a value of 1 million, and my long has a value of some incredibly long number here. Now my float, I've assigned a value of 99.99, and I've done that for the example of looking at the quirks with rounding. And my double, I've assigned it an incredibly long value, which just so happens to be the first several digits of pi. Now a couple of things I'd like to point out. With regards to the literals in the primitive types, anything above an int will require a suffix of the type that you're declaring. And so whenever you assign the value to a long, you always need to append to the end an L. You can use a capital or lowercase l, but when you use a lowercase l, it sort of looks like a 1, and so it's not very clear. And so convention shows that most people will use a capital L. And with the float, you need to append it with an F, and with the double, you need to append it with a D. And these are the only data types that this needs to be done with. Here I have myCarLiteral that I have enclosed within single quotes the capital letter A, and then myCarNumerical that I have passed through in the parentheses an integer value. And as we discussed before, every character is represented with an integer value. That integer value comes from the 16-bit binary value of that particular integer. And so the integer 65 actually has a 16-bit binary value that the car data type uses for converting the integer into a letter, and vice versa. And it just so happens that the numerical value for the letter A happens to be 65. And so I've set the car literal to the letter A, and I've set the car numerical to the letter A, just in the two different ways that the car can accept those data types. Moving forward, I also have a Boolean literal, and I've assigned it the value of true. And this is without any quotation marks or parentheses. You simply type in the word true or false, and lowercase will suffice. Now I've also done my Boolean conditional, except instead of passing in a literal value of true, what I've done is I've given it a condition, which I'm using the parentheses to denote, and the condition is my byte is equal to 125. There's a couple of things that I need to explain here. My byte, of course, is the variable that I've set equal to negative 120. This double equal sign is much like the assignment operator equals, except instead of assigning the value 125, I'm asking it, does it equal 125? And so what these parentheses here basically represent is I'm asking Java, look at this condition and tell me if it's true or false. And the parentheses are a conditional that will return a true or false value. And the condition I'm asking is, does my byte equal 125? And that's where you use the double equal signs, is when you're asking, is this equal? And now we know that it doesn't equal 125, and so when we run this program, this should take a condition and convert it to a false, because this is in fact false, and it should set that value false equal to my Boolean conditional. And so the Boolean literal should equal true, and the Boolean conditional should equal false, based on the fact that that is the case. So further down this program, we can see that I am also displaying a couple of headers. I have a header entitled variables, and I'm printing out to the console some literal text, and I've, using the concatenator, included the values of these variables. And so I'm typing out in text byte, and then adding to that the value of my byte, short to the value of my short, integer to the value of my int, and so forth and so on, with my long, my float, my double, character literal, character numerical, Boolean literal, and Boolean conditional. And so this will create a table that will help us see the values that I have assigned up here in a nice organized way. Below that, I've begun a table with the implicit casts, and these are going to be the widening casts. And under that I have the explicit casts, which are going to be the narrowing casts. And so the way that you're going to tell Java that you wish to cast a variable is by using as a prefix in parentheses the type of variable that you want to convert it to. And so here I'm typing in byte to integer under my table, and then I'm concatenating, and rather than just passing through the value of my byte, I'm going to prefix it with the parentheses int and then the value of my byte. And what that's going to tell Java is, before you give me this value, go ahead and cast it to this variable type. Now I've done the same with double for my int. I'm going narrow here. I'm widening these variables. So I'm taking a byte and I'm widening it into an integer. I'm taking an int and I'm widening it into a double. I'm taking a short and doing the same thing. I'm making it wider into a float, and I'm taking a float and I'm widening it into a double. And the reason that these are all implicit casts are because no information is going to be lost, but then again, no information is going to be added. It's just going to give us the greater capacity to have information there. And one thing that I want to point out is, though I have, for the purposes of the demonstration, included these casts right here, with regards to implicit casting, these are actually not necessary. They're not going to affect the program, but I wanted to include them here to make it more clear. But if you are doing widening casts, you will never actually need to explicitly put them there, because it's not an explicit cast. Java will simply take care of the conversion on its own, and you're good to go. Now down here I've done the explicit casts, and these are going to be the narrowing casts. And so I'm taking an integer and I'm narrowing it down to a byte. I'm taking a long and narrowing it down to an integer, and then I'm taking a double and I'm narrowing it down to a float. Now with explicit casts, with narrowing casts, these are going to be necessary, because you're telling Java, I explicitly want these data types narrowed, and I'm aware of the chance of having data loss. And so let's go ahead and run this program so we can see both how this works and then some of the interesting quirks that are gonna show up. All right, so what have we got here? And so the first thing that we'll notice is, just as we've declared the values, they're showing up here in the table. We have the byte equal to what we've assigned the byte to. And I'll actually just pull it up over here so we can line it up. We have the byte equal to negative 120 like we've assigned. We have the short to 129. We have the integer. We have the long. The float is 99.99, and then the double is these first several digits of pi. And so everything here came through just as we were expecting. Here is the car literal, which is a, and the car numerical, which, as I told you before, was the numerical value of a. So those are both showing up as a representation of a capital A. Then we have the Boolean literal, which was literally passed through the value of true. And then if we move this over here, the Boolean conditional, which, as we saw, mbyte being tested to equal 125, which it doesn't, which would convert to a false, which is the value that it returned, a value of false. Now, what's interesting is down here into the implicit casting, well, we're taking a byte and widening it to an integer, and so the negative 120 hasn't changed much. It hasn't lost any data, and it's because it's still an integer and not fractional data, it's not going to add anything extra because, adding more zeros would actually change the value. But here we've turned an integer into a double, and so we've taken a 32-bit integer and we've widened it to a 64-bit double, a fractional data. And so we took the value of 1 million that we saw up here, and it basically kept the same value, but then it added the decimal in the 0. And so the value hasn't changed, it's just made it a lot wider. But notice that we haven't added any information to it. Now here we have the short to a float. So we've taken a short integer of 129 and we've converted it to a fractional data type of a float, and it's done the same thing. It's kept the 129, but it's added a little extra room for us, but not any extra information. So now it's a 129.0. Now here's what's interesting. We had a float that was equal to 99.99, but when we widen that float to a double, it gives us many more decimal places, but this is 99.98. And so what happened here? How did we go from 99.99 to 99.98? And this has to do with the way that Java rounds things, and the rounding errors typically occur because of the nature of binary data. And so it just so happens that some of these quirks will be seen whenever it attempts to convert from integers to binary and then back to integers or back to fractional data types. And so this is technically not correct, although it's pretty darn close. I mean, 99.98999 is almost 99.99, but it's not exactly. And so why didn't it give us 99.99000000? Again, just one of the quirks of Java. And as I mentioned before, there is a data type called big decimal that does take care of this. This would be very important if you were writing a banking app or anything in which those fractional cents would actually add up over time. So you'd want to be very careful, and you do want to be aware that that rounding error does occur from time to time. Now over here we have the explicit casting. So these are going to be the narrowing casts. And so we have an integer of 1 million that we've converted to a byte. And we get 64? Well, what the heck is going on here? So again, because of the nature of it using binary to convert, and binary is just zeros and ones, it attempted to take what it thought was a binary value, a 10000000, thinking that it was like some combination of binary code, and convert that into a byte value, which of course, as we saw before, in reference to the character data, that the letter A does have a binary value. 65 can be represented in binary, and what the character data type does is it will take the 65, it will convert that into a 16-bit binary code, and then convert that 16-bit binary code into the letter A. Well, the same thing has happened when trying to convert an integer to a byte. It assumed that this was binary, not full integer data, and something to do with the amount of zeros after it, and it converted that as though it was binary. And so if you were to try to represent the number 64 in binary, that would be actually how it would look like. And we can prove this by changing the value to, we can actually add a 1 at the end of it, and it should convert that to a 65. And if you don't know exactly how binary works, it's actually pretty interesting. I would encourage you to look it up. But let's add a 1 to that supposed binary series, we'll save this and run this again. We'll compile that, and let's clear the screen and run that. And we should expect to see a 65 instead of a 64, which is what we see. And again, it's because it's regarding that as binary data. It's just an interesting little quirk, and there is a workaround for that, but we'll talk about that a little bit later. Now down here, we are narrowing a long to an integer, so we're taking a decimal value, or I'm sorry, we're taking a numerical value of this many digits, and we're narrowing it in digits, and so we have a 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, and well, what the heck is it? It gives us negative 1949288 That's not even close. And it's the opposite sign. It went from a positive number to a negative number. Well, now what the heck is going on here? Now, there is something called, it's called two-signed conversion. And it's a way that negative numbers are represented in binary by having a leading 1. Tell the computer that this number should be a negative number. And again, this is something, it's called two-signed complement. It's called two-signed complement, and it's a convention of representing signed digits, so negative and positive digits with regards to binary code. And it's something that you can also look up. It's actually pretty interesting and pretty mathematical. And I'll even put a link below the video to a good paper that explains this. But so what it's doing is it's getting confused about, again, the same way that the integer was being regarded as binary data, that this particular number was trying to tell the computer that it was supposed to be actually a negative number in some kind of binary. And so that's where this error crops up. And so it's very important to be aware that these errors happen, and we'll talk about the workaround probably in another video, but just be aware that it is the case. And then down here we see we've taken a double, which was a very long value of pi, and converted it to a float, which would be much shorter. And this one actually came out just right. So we went from a 3.141592653 to a 3.1415927. And it took that 5 right there and rounded that 6 up to a 7, and that's why we wind up with that. And so that I can live with. That's actually going to be a fair value. And so anyway, that's a little bit about casting and about the quirks that will happen with casting, and the workarounds we'll talk about in a later video. Just be aware that those errors do crop up and that they are important to be aware of. Otherwise, I hope everything in this video was entertaining and educational. Can't wait to see everyone back again in the very next video. Hope everyone has a beautiful night, and thank you so much.